All right, so electricity, I know there'll be quite a wide range depending on whether you've done physics in high school or not, because I know that some of this electricity gets covered in NCEA, but I'm just going to go over the quite the basic stuff. So we have, for our first question, we have 3 charges placed at the corners of an equilateral triangle, as shown in the figure below. So we've got a negative charge at the top and a positive charge in the bottom 2 corners. And we want to know what the direction of the force is going to be on the negative charge. So we're going to look at each of these separately. So first we'll look at the negative charge, and we'll look at the positive charge on the bottom left. So negative and positive charges are going to attract each other. So this positive charge is going to exert an attractive force on this negative charge. So the force that this negative charge will feel will be in this direction. Okay, so that's from this bottom left one. And then now we have the other positive charge here. And if we forget about this one here on the left, and we assume that this one on the right is the only positive charge that's around, then the force that this negative charge would feel due to this positive charge would be in this direction. So it's not, yeah, but they should be symmetrical because it's an equilateral triangle. So then you can do vector addition of these 2 vectors. So you've got your one going to the bottom left and then one going to the bottom right. So that's vector addition. Oops, not quite. Yep, and that should go, if you add them, it should go directly down. So the resultant force will be straight down. Okay, so that's a relatively simple one, but it's critical that you understand. Number 2, we've got 2 small metal spheres with an electric charge of 1 microcoulomb each, and they're positive. They're placed 0.3 meters apart with no other charges nearby. What is the force between them? So the force between them will be an electrical force because they're both positively charged. So electricity is basically all about positive and negative charges. It's about the movement of those charges and trying to understand the forces involved in them and the energy, electrical energy. Okay, so the equation for electrical force is force is equal to K. So K is an electrical constant, and then you've got the charge of the first charge, and then the second charge over R. So R is the distance between the 2 charges, R squared. Okay. And K is equal to 9 times 10 to the power of 9. Okay, so that will be on your formula sheet. But I would just write that down on your cheat sheet as well. But by the time you get to the exam, you're probably going to memorize that number. So if we substitute our values in here, we've got K, which is 9 times 10 to the power of 9. We've got Q1. So Q1 and Q2 are both 1 microcoulomb. So we're just going to put it in brackets. 1 times 10 to the power of negative 6 squared, right, because there's 2 of them. And R, so that's the distance. So that's 0.3 meters. 0.3 squared. And if you plug that into your calculator, you're going to get 0.1 newtons. Okay? And since they're both positive, they're going to be repelling each other. Number 3, we have how far apart must two protons be if the electrical force between them is equal to the weight of a single proton located at the surface of the Earth in meters. And they've given you the mass of a proton. So sometimes they'll give you these problems without giving you the mass of a proton, but you should remember that on your formula sheet, they are going to give you the mass of the proton. So that formula sheet, it has the mass of a proton, the mass of an electron, the charge of a proton, and the charge of an electron. So if they ever give you questions involving protons or electrons, and you don't know the mass or the charge, you can just look at the formula sheet, which is going to be at the front of your exam paper. Okay, so it's important to remember that. So in order to solve this question, we need to know the mass of a proton, which we've been given, and that would be on your formula sheet anyway. So we'll write down the mass of a proton, which is equal to 1.67 times 10 to the negative 27 kilograms. And then we need to know the charge of a proton. So the charge of a proton is going to be positive 1.6 times 10 to the negative 19 coulombs. Okay, so coulomb is the unit of charge, and as you can see, that's a very small number. Okay, so one proton has a very small amount of charge. Okay, and I know that people get confused about this because when you do chemistry and an ion is missing an electron, you write down the charge as +1, right? But the unit, that just means that one electron is missing. The actual charge on that ion is going to be 1.6 times 10 to the negative 19 coulombs, right? So just keep that in mind, and I find that people always get confused on that one. So we've got our equation for electrical force. So we need the electrical force to be equal to the weight of a single proton. So that's just going to be, so the weight force of a single proton is going to be mass times gravity, right? So 1.67 times 10 to the negative 27 times 10. So that's going to be 1.67 times 10 to the negative 26 newtons, and that's going to be equal to our electrical force. So now we need to rearrange our electrical force to find R, which is the distance between the two protons. So if you do that, so if you look at I've uploaded my cheat sheet for electricity, optics, and radiation as well on my Google Drive. So on there I have this equation rearranged for all of the variables because it's quite common that they ask you this. So we have K, Q1, Q2 over F, right? So then we just have to put our numbers in. K is 9 times 10 to the 9. Our charge, Q1 and Q2, they're both 1.6 times 10 to the negative 19. So we're going to put a bracket around that and square it. And the force is going to be 1.67 times 10 to the negative 26. So that would be 0.12 meters. Okay. So this equation here is just the previous force equation for electricity rearranged. Okay, so our next question, number 4, is more of a conceptual question. And this type of question is quite common. So it's worth spending a bit of time on this to make sure that you understand it. 2 point charges, Q1 and Q2, are held in place 3 centimeters apart. The magnitude of the force on Q1 due to Q2 is found to be 4 newtons. And then they're 1.5 centimeters apart, so the distance between them has halved, so they've gone from 3 centimeters apart to 1.5 centimeters apart. What's the force on Q1 due to Q2 in this new configuration? So what do you think will happen if you have 2 charges and you halve the distance between them? Is the force going to get stronger or weaker? It's going to get stronger, right? So if you halve the distance, if they're twice as close, is the force going to be doubled? No, so it's actually going to be quadrupled, so it's going to be increased by a factor of 2 squared, which is 4, okay? And the reason for that is because if you look at the equation, force is equal to K times Q1 times Q2 over R squared, okay? So what that means is that force is inversely proportional to the radius, the distance squared, okay? So let's have an example here. So let's say that initially our radius was 1, our R was 1, so force would be equal to 1 over 1, which is equal to 1, right? 1 Newton. And then you're going to halve R. Oh, sorry, so this should be 1 squared. So 1 squared is just 1. 1 over 1 is 1. And then you're going to halve the distance, so it's going to become 1 over 0.5 squared. So if you do 0.5 squared, that's just half times a half, which is 1/4, right? So that's 1 over 0.25. And if you did 1 divided by 0.25, that's going to be 4. So you can see there that the force has quadrupled, okay? And then if you were to, say, make the distance, decrease the distance by a factor of 3, so that would be 1 over 0.33 squared. That would be 1 over 0.1667, and that would be 9 newtons. So if you decrease the distance by a factor of 3, the force is going to increase by a factor of 3 squared, or 9, okay? So it's very important to understand that. So what that means for our problem is that since the original force was 4 newtons, it's going to be quadrupled, and the new force will be 16 newtons, okay? Okay, so number 5, we have 3 charges arranged in a line. And we know that the net force on Q2, so we've got Q1, we've got Q2, and we've got Q3. So we don't know what the charge is on any of these. We don't know whether they're positive or negative. But what we do know is that the net force on Q2 is 0. So what that means is that Q1 is going to be exerting a force on Q2, and Q3 is also going to be exerting a force on Q2. So just for this problem, let's say that Q2 is negative, And let's say that Q1 and Q3 are positive. Okay, so Q3 would be pulling on Q2. So this is the force from Q3. And this would be the force from Q1 on Q2. Because remember that positive and negative will attract. Okay, and because the net force is 0, these have to be, the force has to be equal to cancel each other out. What we do know is that the distance between Q1 and Q2 is double the distance between Q2 and Q3. So that's 50 centimeters, and that's 25 centimeters. Okay. So in order for the force to be the same, if the distance is doubled, the charge is going to be the charge is going to be 4 times greater, right? So Q1 has to be equal to 4 times Q3, right? Because if they were the same charge and it was twice the distance away, the force would be 1/4. So in order to overcome that, in order to compensate for the double the distance, it has to be 4 times the charge. Okay, and it's going to have to be the same sign as Q3. So it's going to have to be the same sign, which is positive, right? So this one's plus 4 Q3. If this one was negative, then it would, let's say if this one was negative, then you'd end up with another force pushing it away. So then the net force wouldn't be 0, okay? Question number 6. Again, we have the same sort of arrangement, slightly different question. We have a plus 40 microcoulomb charge at point A and a negative 10 microcoulomb charge at point B. And we have an unknown charge at point C. So the distance between these two is double the distance between here and here. Right. So that's 4 meters. And that's 2 meters. Okay. So again, we know that the force at point B has to be 0. So this charge is going to be pulling on the negative charge. And so that means that this charge, this unknown charge, has to be positive in order to exert a force to the right. And because it's half the distance, it only needs to be 1/4 of the charge to exert the same amount of force. So it's going to be 1/4 of 40. So 40 divided by 4, which is 10. So it's going to be positive 10 microcoulombs. Okay? And if you go through the past 10 years of exams, there's probably about 4 or 5 of these. So pretty much one every other year. So it's good value getting to know this one because it's highly likely to come up. And it's quite easy to solve because you don't even need to use your calculator, right? As long as you just understand that the force is proportional or inversely proportional to the r squared. Okay? Number 7, a conductor is charged to negative 6.9 times 10 to the negative 3 coulombs. How many excess electrons does it contain? So what we've been given is the total charge, the total negative charge. So the symbol for charge is Q. So Q total is equal to negative 6.9 times 10 to the negative 3 coulombs. And in order to solve this equation, in order to solve this problem, we need to know how much charge one electron will have. Okay, so that's going to be on your formula sheet at the front of your exam paper. And the charge of one electron, so Q of an electron, so electrons are negative, is going to be negative 1.6 times 10 to the power of negative 19 coulombs. So you'll notice that the charge on an electron is the same magnitude as the charge on a proton. It's just that an electron is negative and a proton is positive. Okay? And you should also know that the mass of an electron is going to be, but the mass of an electron is going to be different to the mass of a proton. So mass of an electron is much smaller. So if we know the charge on one electron, we can just divide this total charge by the charge on one electron to find out the number, because the total charge is going to be equal to the charge on one electron times the number of electrons, right? So that's the number of electrons. So if you rearranged it for the number of electrons, that's going to be Q total divided by Q of electron. So negative 6.9 times 10 to the negative 3 over negative 1.6 times 10 to the negative 19. And that would be 4.3 times 10 to the power of 16 electrons. Okay? So pretty simple. As long as you can remember that you do know the charge of an electron. Number 8, we have a 54-gram ball of pure aluminium, which has a charge of positive 32 microcoulombs. Each aluminium atom has 13 protons, and aluminium has a molar mass of 27 grams per mole. How many electrons have been removed from the aluminium ball? So this one seems quite a lot harder than our previous question, but in essence, they're exactly the same question. So all you need to know is the total charge in order to find out how many electrons has been removed. So remember that if you remove an electron, it's going to become positively charged, right? So we're going to do the exact same thing as we did before. We just need the total charge, so Q total, which is equal to 32 microcoulombs, or 32 times 10 to the negative 6 coulombs. And we need the charge of one electron, which is negative 1.6 times 10 to the negative 19 coulombs. So again, we're just going to divide the two numbers. So 32 times, in total, 32 times 10 to the negative 6 over 1.6 times 10 to the negative 19. Okay. And that's going to be 2 times 10 to the power 14 electrons. Okay. So that's just a good example of them giving you lots of unnecessary information. You just need to look at, that's why it's so important to identify what you're actually looking for and what other variables you're going to need in order to solve that question to prevent you from becoming flustered. Number 9, what's the final kinetic energy for an electron accelerated in an electron gun from rest at 0 volts to 1000 volts in joules? So volts, have you guys had the lecture on electric fields yet? You guys learned about potential differences and voltage? Yeah. Well, I'll go through it quickly again. So if you have a positive charge, let's say you have all these positive charges lined up on the left here, and then you have all of these negative charges lined up on the right. That's going to create an electric field. Okay, so if you put a charge in the middle of here, it's going to feel a force. So the direction of the field is always going from positive to negative. Okay, so the direction of this field, this electric field, will go from left to right. So it's going from positive to negative. Okay, you need to remember that, because it'll come up in your exams. So these electric field lines will go from left to right. Okay, and so in our question here, let's say that this scenario here is for our question, this electric field. So the more positive you get, the higher the voltage. Okay, so 1000 volts will always be on the positive side. So let's say this here is 1000 volts, and this side here is 0 volts. So remember that the positive side will always have the higher voltage, and the negative side will always have the lower voltage. Okay, and an electron is negatively charged. Okay, so if you want to accelerate an electron, where would it need to be? Would it have to be on the left or the right? On the... Yeah, so it'll accelerate towards the left, so it needs to start at the right. So our electron, which is negative, will start off at the right plate, and it's going to accelerate towards the left, right? Because it's going to be repelled by the negative charges and going to be attracted to the positive charges. Okay, so we can, if you just drop this electron here, it's going to start moving. So initially it's going to be at rest, and then it's going to start to accelerate because there will be a net force on the electron, and that's going to cause it to accelerate. And when it gets to this point here, so when it goes from 0 volts to 1000 volts, it's going to be going at a certain velocity, which means that it will have kinetic energy, right? So we want to calculate the amount of kinetic energy, and the kinetic energy will be equal to the electrical energy that it's gained. Okay, so the electrical energy symbol is U, and the equation for electrical energy, U, is equal to the charge, Q, times the voltage, or the potential difference that the charge has traveled through. Okay, so in this case, it would be the charge of the electron and the voltage, or the potential difference, which is 1000. Okay, so the charge of an electron is negative 1.6 times 10 to the negative 19 times 1000. So that's going to be 1.6 times 10 to the negative 16 joules. Yeah, and remember that energy is a scalar quantity, so it can't be negative. Oh, well, it can, but yeah. In this case, we're just looking for the magnitude. Yep, okay. So then number 10. Number 10 should be pretty easy. So if we look at option A, we want to find the diagram that's accurate or correct. So if we look at option A, we have field lines going, sorry, I'll just rub this off. So we have a positive charge, and we have electric field lines coming in to the positive charge. So remember that I always said electric field lines go out from positive. So option A is wrong. Option B is also wrong because there's lines going out from negative charges, so it always goes in towards negative charges. Option C, you've got lines coming out of the positive charge and lines going into the negative charge. So option C is going to be a correct answer. Okay. Option D is showing your equipotential lines. So at those lines, everything's going to be the same voltage as you go along those lines. So that's why it's called equipotential. So equi means the same or equal, and potential for the potential difference. Okay. And then, yeah, E's wrong. So even though the what's happening there in E is wrong because it shows that the electric field lines aren't interacting with each other, but if you have two charges, they're both going to influence each other. Okay. And number 11, we've got electric field lines caused by two charges. And we want to find the following statements that is true. So option A. So if you look at Q1, is it going to be positive or negative? It's going to be positive, right? So Q1 is going to be positive. And is Q2 going to be positive or negative? Negative? Right. So Q1 is positive. Q1 is positive. And Q2 is going to be negative. Okay. And how can you tell which one has the greater magnitude of charge? Sorry? Yeah, the line. So the greater that, the greater the electric field is, the more lines you'll have coming out of the charge. And the greater the charges, the greater the electric field will be. Okay, so Q1 obviously has more lines coming out of it than Q2. So Q1 will have the greater magnitude of charge. Okay. So the option that's going to fulfill those criteria is going to be option D. So Q1 is positive, Q2 is negative, and the magnitude of Q1 is greater than the magnitude of Q2. Okay. So we have finished the basic tutorial. That was pretty quick. So I'll start the next one at 20 past. So 8:20. Okay. And the advanced one should be a pretty quick one as well. Okay. All right, cheers.